Hi, this is Dr. Tyagarajan, Professor in ECE Department of RMD Engineering College. In this video, I am going to explain the internal bus architectures, the signals used with buses, and bus arbitration. Bus is a group of wires through which address or data or control signals are transmitted. If a group of wires transmit 32-bit address, then it is called as 32-bit address bus. All devices share the same address bus. Similarly, they share a common data bus. A control bus transmits all control signals, that is read, write, memory, etc. to control the devices. You see this figure, the CPU, memory and secondary memory disk all are connected to the same bus, same group of lines. For example, you take this address is A0 to A31. That means 32 bits are used. That means 32 lines are used through which the address is passed. So these 32 lines form the address bus. Similarly, here we have data lines from D0 to D63. That means 64-bit data bus. So all the 64 bits will be transmitted through these 64 lines, group of lines. So that is called as data bus. Similarly, all the control signals form the control bus. Here control signals means read, write signals and memory signal or IO signal, etc. Similarly, all the power lines are grouped together and it will form another bus. So, this is the simplified illustration of a bus. Based on type of communication, there are two types of buses. First one is synchronous bus. Another one is asynchronous bus. In synchronous bus, each operation is synchronized with bus clock. In this type of buses, only devices which are faster than bus speed can be used. In the case of asynchronous bus, the operations use handshake signals. Both faster and slower devices may be connected with these buses. This is an example for synchronous bus. It is internally used in the microprocessor. See, this is the clock signal. When the clock is changing from low to high, it forms a leading edge. Similarly, when the clock is going from high to low, then a trailing edge is formed. Now we are taking 3 clock cycles and we will see how the operations are synchronized. Here, this is address bus. This type of representations with the 2 lines like this will indicate that this is a bus. So, this is an address bus. Similarly, this is data bus. Here, this line indicates a single control signal. Since it is a memory request, it is a control signal. And this signal is active low signal. That means this will work. That is, memory request will work during this low period. Similarly, read is another control signal. This will be active when it is low. Active means it will work only when it is low. When it is high, there is no read operation. That is the meaning. Each signal is synchronized with the clock. For example, this address will be put on the address bus only after this leading edge. That is, after this leading edge, the address will be put on the address bus. And after trailing edge of this T3, it will be closed. The data will be placed during the T3 clock cycle. So, first address is placed during this T1 clock cycle, and a memory request signal is also activated during this period. Now, since the memory is connected to this address line, it will receive the address, and to indicate that only memory should access the address, this signal is also asserted low. So in this case, the memory will receive the address, but with this signal, the memory will not know whether it is a read operation or it is a write operation. For that, the processor will issue read signal during T1. That is, after giving the memory request, it will give the read signal. So, the memory gets the address and it knows that it is a read signal. That means the CPU wants to read from the memory. So, the memory will put the data on the data bus. Then it will be available only for a small period. Within this period, the CPU will read the data and it will make this memory request high. That indicates that memory read operation is over. Then this read operation will also be made high. So all these things will be happening or synchronized with these edges, that is with the clock cycle. Then next one is asynchronous bus. It is also for read operation. In asynchronous bus, first the CPU, that is microprocessor, will place the address on the address bus like this. Then it will assert the memory request like this. It will assert means it will make it active. It will assert this signal low. So the memory will get this signal. Then read signal is also used. So the memory will understand that it is a read operation. After that, the microprocessor will issue a master synchronizing pulse. That is happening here. This edge, the trailing edge of this master synchronizing signal, will activate the slave synchronizing signal in the memory. So, the slave synchronizing signal edge appears here. During this time, the data will be put on the data bus by the memory. After this, master synchronizing signal will be asserted high. That means it will be deactivated. And read signal will also be deactivated. So during this period, at these points, the read operation should be over and memory request signal will also be asserted high. Then address lines will be closed. So when the master synchronizing signal is asserted high, it indicates that the slave synchronizing signal should also be closed. That means it should be asserted high and the data line should also be closed. So with these signals in a handshake mode, the data will be read. This part of the video explains the bus arbitration. When many devices want to put address on the same address bus, that is, if more than one devices want to be a master, then bus arbitration problem arises. There are four methods available to solve this problem. The first method, it is a simple centralized bus arbitration method. It uses an arbiter to control the bus request and bus grant. In this case, if there are n devices, all these devices will be connected to a single bus request line, and this bus request line will be connected to an arbiter. If any one of these devices wants to be a master, then it will request through the bus request line, and the arbiter will send a bus grant line. That bus grant line will pass through these devices in a daisy chain. That means the output of the first device will be connected to the second device. So like that, all the devices will be connected like this. In this case, the bus grant signal provided by the arbiter will pass through the first device. If it has requested to be a master, then it will accept that bus grant, and it will not pass the bus grant to other devices. If it has not requested the bus, then it will pass this bus grant to the next device, and the same thing will be repeated. If the next device has requested the bus grant, then it will accept it and it will not pass to the next device. Otherwise, it will pass the bus grant to the next device. So in this case, the device which is closer to the arbiter will get highest priority, and the device which is very far from this arbiter will get lowest priority. So this is a disadvantage. To solve this, another method is proposed, that is called as centralized arbitration with priority levels. So here again there are n devices, but these devices are not connected to a single bus request line. Instead of that, there are k number of bus request lines. Now bus request level 0 is connected with device 1 and device n. Similarly, bus request level k, that line is connected with device 2 and device 0. So there are n levels for bus request. At the same time, there will be n number of bus grants. So the arbiter will receive the bus request through the bus request lines, and it will issue more than one grant signals. For example, if it issue grant signal for level 1, that will pass through the device 0. But the device 0 is not connected with bus request level 0. So it will just pass this to this one, device 1. Since the device 1 is connected with bus request level 0, the device 1 will check the bus grant. If it has requested, then it will use that bus grant, and it will not pass the bus grant signal to the next device. If it has not requested, then it will pass to this next device. But anyway, that is not connected to the bus request level 0. So the device 2 will not accept that. It will pass to the next one. And only the device N has been connected to this bus request level 0. So it will accept. So here the devices which are connected to level 0 will be given highest priority. So in this case, device N will have highest priority compared to device 1. So this arrangement helps to fix the request level and priority for different devices. In the third method, a centralized arbiter is used and it is called as fully centralized bus arbitration. Here, all the devices will have separate bus request line and a separate bus grant line. All the bus request lines will be connected to the arbiter and the arbiter will issue the bus grant signal individually to all devices. In this case, any device can request at any time and the bus grant signal will be provided by the arbiter and the arbiter can decide the priority. So any device may be set with any priority. Now all these three methods are using a centralized arbiter. So these are called as centralized bus arbitrations. In the fourth method, no arbiter is used. Here, instead of that, a busy signal is used. So, all these devices are connected in a daisy chain mode. If a device, for example, device 1 wants to be a master, it will issue a bus request signal or it will assert the bus request line and it will also issue a 0 signal to next hired number devices through the daisy chain. That means they may not get bus grant signal. Then it asserts the busy signal and de-asserts the bus request signal. When it issue the busy signal, no other device can request the bus. So, in this method, large number of devices may be connected. But in the centralized schemes, only small number of devices may be connected.